So we have a big task ahead of us today, which is discussing how these star systems that we've been working our way through. No?
1 cup.
1 cup. All right. Better than nothing. Thank you, sir. Whoa. All right, thanks, man. All right. So we have, like I was saying, last week we made it through. We made it up to this basic idea of how stars are formed, right? Which is a lot more nuanced and complicated than a cloud of gas crushing itself into a star. There's a lot of chemistry. There's a lot of temperature dynamics, just like storms, and there's a lot of electromagnetism that's going on. And so these things conspire to a point where gravity can take over because you have so much material in one place. It's all pulling on itself, pulling on one another. And this is our best idea of how stars are formed. You might have noticed it's a rather hazy story, and that's because the details are still being worked out. Now, unfortunately, the story of how planets are formed is much, much worse than the story of how stars are formed to some extent, okay? So the story that I'm going to tell you today of how stars are formed, the one that's in your textbook, is essentially a story that's about 300 years old. And as one might expect with a scientific story that's 300 years old, it's probably in desperate need of an update. And there's some really interesting pieces of the story that I think point us towards how that update's going to happen. So I want to do 2 things in my attempt to answer the question with you guys today. How are planets formed? And to do that, I think what we're going to do is look at all of the data that we have, all the evidence that we have, which is all very, very recent. We've only been able to see other planetary systems for 10 or 20 years. And then we're going to look at how these new pictures fit into the models that we've been working off of for a few hundred years. And then we're going to think about other things that could solve some of those problems. So I'll present some sort of radical ideas to you, which might be the horizon of what is being developed in the future. That could be really exciting for any of you who go into these fields, or maybe it's just exciting in general, because change is always exciting. I do want to say, though, this planet concept is really quite interesting by itself, and it's worth understanding. Just very briefly, I don't want to derail this lecture completely into the ancient ideas, but the word planet is a Greek word that, well, it's not exactly a Greek word, but it's derived from the Greek word for wanderer, which is interesting by itself, but how the Greeks thought of and how the ancients in all these civilizations thought of their planet is really quite interesting. And I think that it tends to explain why we've been left with the model we have for planets to some extent too. I'm going to make that case for you. So, when people looked up at the stars in the past, they noticed, this is thousands of years ago, they noticed that some of the stars moved, first of all, which was very strange. In other words, they didn't just move with all of the other stars, because of course, if you go and stand and watch the stars at night, the Earth is turning and the stars all appear to move. But some of them were moving from night to night. They were in a new position. And even more disconcerting was some of them moved backwards every once in a while, right? This was absolutely perplexing for thousands of years. And what the ancients did with these particular stars that moved backwards, which we now know are the planets, is they assigned their sub-gods to these entities, right? So often you'll have a central god, which is often the sun, but we're represented by the sun. But you have these sub-gods, right? Now, first of all, why are the planets moving backwards, right? Well, it turns out that when the Earth moves past one of the outer planets, it overtakes it in its orbit, right? These planets on the outside move very slowly, so we'll overtake Mars. So it could look like Mars is in front of us at some point, and then all of a sudden it's moving backwards. It's not really moving backwards, of course. We're just in orbits, which no one had really articulated for another, 2,000 years after that point. So there's these wandering gods in the sky, right? And this is not such a primitive idea. And I want to at least remind you of the Jungian concept, I think Jung did a great job of trying to make sense of what these ancient stories meant and why we had them and why they persisted for thousands of years. And the idea was something like you have a series of understandings that are built into you, right? There's things that you understand that no one ever had to explain to you, and that's pretty crazy if you think about it, right? And some of those things are what the ancients represented in the planets. So if you think about something like Mars, Mars is actually the god of rage. Well, rage is an interesting thing to understand because no one needs to explain to you what it means. If someone says, I'm angry, you don't say, well, what does that mean, right? Or how about love, Venus? No one needs to, you don't have to explain to your friend what it feels like to be in love. I mean, you might try, and poets have wasted no ink attempting to explain it, but actually getting at these things in some sense is impossible. They're so fundamentally baked into our experience as human beings that we don't even possess the means of articulating them because they happen in a sense before our thoughts can convene. And this is really troubling because what it means is that in some sense you're really an assemblage of all of these different pre-programmed ways of experiencing the world. And this is actually extraordinarily important in the modern landscape because the challenge of being a human being in society to some extent is to put all of those pre-programs under the control of one overarching entity. And that's essentially what we call I, me, myself, I, the one who is deciding not to give in to the anger that's possessing me or give in to whatever at any given moment, but to subsume all of those emotions, right? Now, the ancients, I think when they assigned those sub-personalities to these gods who happen to be wandering in the sky, this wasn't an accident. Because, as you know, these sort of emotional experiences of our perception, they're often chaotic, right? You can be traveling along in your life, you can be just studying or something, and if, for whatever reason, something unexpected happens, you might be possessed by one of these sub-programs in a way that absolutely subverts your entire experience. It's very chaotic to find yourself angry all of a sudden about something. It's very unsettling, right? It's not predictable in the same sense. You don't realize you're going to become angry until you are, or you don't realize you're going to fall in love until you do. So why does this matter in terms of astronomy? It matters because the models that the Enlightenment thinkers came up with, which are essentially the ones that I'm going to present to you today, for how planets operate, and let's say how they form, where they come from, what they are, essentially, what that phenomena means, is an extraordinarily ordered concept. It's actually ordered to a fault, and we'll see that. So the ancient idea of these wandering, chaotic planets was something that the Enlightenment thinkers were adamantly opposed to, right? They wanted to describe nature as if it was this ideal utopian system that was absolutely ordered, right? This is really important because, of course, it led to all sorts of tyrannical repressions in the Victorian era and the times that followed, right? But it's interestingly enough led to some parallel crises in our science of how the planets work today. Because what happens is if we treat the planets like they are part of some idealized ordered structure, which is nature, then all of the solutions for how the planets formed, how they process, how everything works in our solar system is going to be based on the preconception that nature should be this beautifully ordered clock that works reliably all of the time. And we didn't make room in our theories for chaos. We didn't make room in our theory for, well, maybe that planet hasn't always been there, right? And so the bleeding edge of planetary science is now starting to entertain, it's starting to reintegrate some of this chaos into the mix. Well, we can't make sense of what we see through our telescopes anymore in terms of what we thought for hundreds of years. And this has happened in the last 10 or 20 years. It's really, really the cutting edge. Because We see huge gas giants very close to stars. Their atmospheres are getting cooked off. It's a very, very dynamic system. And this is not at all like what we had thought was the case. So I think that understanding a bit about how human beings have thought about these things for thousands of years actually is completely relevant to the way that people think about them today, in that there was a reaction to that, and now there's a counter-reaction. And culture works like that, right? Culture is constantly taking a right foot forward, a left foot forward. We're always trying out the different extremes of our perception as we go through the world. And science is no different. Science is, in fact, hardly distinguishable from culture itself. Of course, we hope that it's grounded in the most empirical, objective observations possible, but it turns out that humans are almost incapable of objectivity. I would say we're fundamentally incapable of it. In fact, everything that we do is based on something that is processed by our perception. We don't just see things, we see what we expect to see. There's a really famous experiment I would just want to tell you about that proves this point out if you don't believe me. There's this gentleman, gosh, what was his name? I won't think of it. He was a Harvard psychologist. He did this experiment where he did two really funny experiments. Let's tell you both of them. So the first one he did was, at Harvard, at any of these universities, maybe they do it here too, you'll see tours of people going through, right? People get lost. They're like, which way is the dining hall or something? And so some friendly undergraduate will usually, step up and point them in the right direction. Well, they did this experiment where they would set up an undergraduate to be out there to answer questions for people who are lost. And then just as he or she was explaining where X, Y, and Z was on a map, another group of students that were pre-planted would come by. They're moving a piece of furniture, right? And say like a large chalkboard or something. And they would do something kind of rude. They would go right in between the people that were engaged in this conversation. And then they played a really funny trick. One of the people who was carrying the big chalkboard would swap out for the person who was holding the map and explaining it to the person. And in something like 75% of the cases, the person who was being explained to didn't notice that it was a new person who was standing there in front of them. This is crazy, right? You would think, I would never do that, I would notice. But you wouldn't, because when you are paying attention to something, in this case, how to get to where you're going, the details of the situation, which undergraduate it is that's talking to you, is completely irrelevant. And so our entire perception is structured by what we're trying to achieve at any given point. And science isn't immune to this. Whatever we're trying to achieve is where our laser focus is at. That same guy did another experiment that was really funny, where he made a film of people, exiting an elevator. And he said, I want you to count. They had a basketball, and they were passing it amongst themselves. No, this is a different experiment. All right, they were all dressed in black or white, and he said, each time the elevator opens, tell me how many people in black are coming out of the elevator. So the undergraduates who are doing this experiment, they count them. They say, well, there was 7 of them in this run, and there was 6 in this run, and so on and so forth. And the investigator says, very good. Did you see anything weird that happened while you were doing this? And they're like, I don't know. What do you mean? And he's like, well, did you see the giant gorilla that was standing in the elevator with them? And they're like, what are you talking about? What gorilla? And he plays the tape back, and sure enough, there's a gorilla just sitting there in the back, right? I mean, it's obviously a man dressed as a gorilla. But the point is, if you're not tasked, if your focus of your attention isn't on the possibility that something unexpected is going to happen, you're not going to notice it. And so much of what we're going to talk about today is very much suffering, as it must, because this is a human condition. We necessarily suffer the consequences of our laser-focused attention on how things should be, what we expect them to be, versus the data that maybe doesn't fit into that, which is really troubling. So anyways, that's the setup for this story today of planet formation. And hopefully by the end of it, we'll make our way into something approaching a sea of possibilities for what could be actually happening. So to do that, we're going to talk about what we can see. And mostly what we can see in the last 10 years is these planetary discs, these, we say, protostellar disks. So around these new stars in these nebula that we were talking about last time, there's these dusty disks that appear. Now the dusty disks are troubling because, of course, dust obscures the light and the heat that we need to actually be able to view the planets. So we can't see a planet forming, which is very troubling. So we don't have the one piece of information that would actually solve the mystery for us once and for all. But we do understand the dynamics of these disks, and those can give us some clues. So we'll go through those. We've also been able to study some of these planets once they're formed in these systems, right? Once the dust has cleared, we can see some of these planets. We call them exoplanets, which is a relatively new concept. You know, when I was in high school, they had never seen an exoplanet before. It was just a tantalizing possibility. Maybe other star systems have planets. That was actually the way people were thinking. Maybe, right? They hadn't seen them yet. In fact, if you would have said for sure there are, somebody would have pushed back against you and said, that's ridiculous. We've never observed one before. And so you have to be very careful with the statements and the judgments that we make based on what we can't see, because just because we haven't seen something doesn't mean it's not there. So we have to keep our minds open as scientists. All right, so essentially 300 years ago, this gentleman, Swedenborg, first proposed what we call the Nebular Theory, which is essentially what we're left with today of how planets are formed. And it's a continuation of the story that we started last week, right? Essentially, these nebula collapse. They form a disk. The disk collapses into these little nuclei that become the planets. Immanuel Kant, by the way, Swedenborg and Kant were both philosophers, not scientists in the sense that you would think of them today. They weren't laboratory scientists. They were just thinkers, which is quite interesting that the standard astrophysical model of solar system formation would come down to philosophers 300 years ago. So Kant proposed this. He published this book called Universal Natural History and the Theory of the Heavens, where he essentially laid out this idea that gravity collapsed these nebula, and that made the stars and planets. Now, that was a very popular model for a while, a couple hundred years or so, but some serious crises arose within it, and they still are with us. And actually, the crises were so bad in the end of the 18th century that people actually said there's no way this nebular collapse thing could happen. And the reason for that is that when the entire story that we've been telling you so far concerns the idea that when you collapse something, even a figure skater or something, there's a spin that appears, right? If there's any rotation in it, which there must be because things aren't static out in the universe, they're in motion. And as these things collapse and twist, they spin really, really fast. And essentially, this is how we get all of that material in one place to make a star in the first place. Remember, in order for those really dense cores to kick over into the density necessary for star formation, you need something like 10 with 20 zeros times the more density than you have in these cores. Something else is happening. And that something else we think has to do with the spin dynamics, the vortex, the massive twisting and compacting of that material. Okay, that's a cool idea. The problem is, if you look at something like our solar system, the sun is hardly spinning. However, the planets are whipping around really fast. Now, the quantitative way that scientists use to describe that is the concept of angular momentum. That's just essentially how much material is spinning around at any given time. Well, in our solar system, for instance, Jupiter has most of the angular momentum. It has most of the material in motion in our solar system. Now, this makes very little sense in terms of the disk collapse model, because what should be happening under this model is that the sun should be spinning at lightning speeds, and the planets that are further away should just be sort of tagging along in a slower form, right? But this isn't what we see, and this isn't what we see when we look out and look at other star systems as well. Okay, so this crisis was so bad that people threw this model out for 100 years after that. They were like, there's no way this is what's happening. And they tried on every permutation they could think of what else could be causing this to happen, and none of those worked either. And so not until something like the 1970s did somebody come along and mathematically rescue this disk collapse model with the angular momentum crisis. And they proposed different situations by which the dust could slow down the star, right? There was frictional interactions that were capable of slowing it down. So this was an entirely mathematically derived theoretical justification for the old model, actually. And this is the one that we're essentially left with today. And it probably would be totally fine if we hadn't looked out into the stars and seen other problems too. And there's one more crisis that crops up too, which is that in order for you to make a planet, let's say just to make a simple rocky, like a big chunk of rock, like Ceres, let's say, which is essentially a planetesimal. In order to make something like that, you have to stick together smaller pieces of rock, right? Well, that's pretty easy to do using the laws of gravitation if you have a bunch of boulders. You can actually stick a bunch of boulders together in a rotating disk. They'll kind of gravitate together over, thousands and millions of years. And you'll get a little planetesimal. Okay, fine. But how do you make a boulder? That actually turns out to be an insurmountable problem for astrophysics. The problem is you can make little dust grains that collapse. You can even make little things that are on the order of a centimeter, little loose chunks, clumps of material. Gravity is capable of this. But how do you get those little pebbles to stick together into boulders? Because when we try to simulate this, the pebbles just pop off each other. They just bounce off each other, right? And so the difficulty is getting something that looks like a planet to form out of a bunch of pebbles. It's virtually impossible. So this crisis hasn't been solved. The angular momentum crisis has some redress, but it's still very much an issue. And so I think when we look at these issues, they're really exciting because they tell us the places where this model is going to perhaps be renovated in the future. And that's the work of the next generation. And of course, science is nothing if not something progressive that's constantly evolving. And we hope to move towards better understandings of how things work in the universe going forward. So, and then of course, another issue too, which I haven't really seen written about too much, but I think it's worth pointing out to you, is that this thing that we're standing on, this planet, is something like 5 times more dense than the sun, okay, on average. Actually, the Earth is the most dense body in the solar system, with Mercury playing a close second. But why is it that these extremely dense things aren't in the center of the pool? Why aren't they in the center of the cloud, right? This doesn't totally make sense with our model either. And so there's some pieces that are out of order here. And it's our job to make sense of those. So let's go through and look at everything we do know now, and then we'll revisit this issue at the end and see if we can't think of some other possibilities. Because this nice idea that these systems all form the way that they look when we look out at our solar system is a very beautifully ordered and reliable and comforting idea, but it might be lacking the requisite chaos that's necessary to make sense of the data. And so we'll deal with that. Cool. So for starters, one thing we do know for sure is that there's these dusty disks swirling around, right? And we can see these now in the last few years, which is pretty cool. I got a couple Hubble images up here for you, which is actually just 4 different disks that are swirling around in our good old Orion Nebula. And you can see that these dark disks are silhouetted against this glowing gas of the nebula in the background, which is pretty cool. So they're quite easy to see. Each one of these disks is about 30 times the diameter of our own planetary system. So they're quite large initially. And this gives us reason to believe that they do change and they are collapsing over time. And then that little glow at the center is, of course, the little protostar, which is thought to be only maybe 1 million years old or so. So this is our starting point. This is where we are working from in order to move towards this model. So far, so good. It does appear that these stars do aggregate disks of material around them. That much seems to be apparent. And I think that's a good starting point. Let's see what else we have here. So we can also see how these disks change with time, which is pretty cool. And what we do is we can use that HR diagram, which we talked about before, to make some estimates of how things, how the timetables change with respect to the development of these systems. So we measure the temperature and luminosity of that protostar, and then we can pop it on the HR diagram somewhere. And we'll look at that in a second in more detail. But what we do see is that if the protostar is pretty young, its disk extends all the way out to hundreds of AU away. But in the older ones, we find that there's still a lot of dust, and the inner regions seem to have lost a lot of that cloudiness, right? So there's some sort of organization, almost a donut shape that appears over time. And then, of course, we have this idea that, well, as the planets grow, they're taking up some of this stuff. They're clearing out spaces in it. And we have actually some evidence that there are ring structures, much like Saturn, that appear. And so this is our first piece of evidence that there are, in fact, planets there. And I'll show you a picture of those in just a second. But, needless to say, if you look at Saturn's rings, right, it has all of these, it has separations in the rings. Well, when we went to Saturn and we looked at it, we realized there was, in many cases, moons, little baby moonlets that were sweeping out those cleared areas, right? So this informed the idea that, okay, when we see these disk structures around these protostars, there are also these pockets of emptiness. Well, that must be where the planets are. And I think that's a pretty reasonable conclusion. Of course, Saturn has banded structures that are independent of the swept out features as well, and those have to do with the different composition and the different density separation and all of these things. Actually, Saturn's rings, we could make a whole class out of it. It's so wildly complex. So there's other things going on as well, but I think it's a reasonable conclusion that at least there's a strong possibility that these gaps that we see in these ring structures have to do with places where planets might be existing. Now, whether the planets are forming there or not is a different matter altogether. Of course, our conception is that star systems form their planets, right? This is something of a pre-existing conception about all this. And so we assume that's where the planets are forming. I think the evidence at least says there's something big there. So maybe the planets are certainly there. Whether or not they're forming there is a different matter. So, I mean, obviously the planets must form somewhere, so we'll have to deal with that as we go along. That's the whole point of this conversation today. So in this picture up here, which is pretty cool, on the left, you can see stars in the infrared. The central star there is much brighter than the surrounding disk. So what this picture over here actually has a shield that blocks out the central star. There's a little block on the lens so that you can see all of the glow around it. And this one on the right actually is modeling of these observations of what these disks could look like once you take out the glow of the star. All right, so here's a picture of what I was talking about. So you can see there's these little banded structures, right? And this is the fundamental piece of the puzzle that tells scientists that there's planets around these protostar systems. In fact, almost, I want to say all, but at least 99% of the protostellar systems that we see have these planetary indications in them. Almost all of the stars that we see seem to have planets, which is really something to think about. The idea is, the theory behind this is that as the planets grow, they're going to stir up the orbits of smaller objects that are around them. And these stirrings, the chaos that results from that, is going to lead to more collisions, more debris being broken up. And then as the things grow, they're going to accumulate more matter. The same thing is going to happen with comets and asteroids. You're going to have a ton of those collisions at first, and eventually it's going to diminish. And actually, we have some of these leftovers, what we believe are leftovers from this process in the Kuiper Belt objects, which are essentially a series of bodies which are just beyond Neptune. In fact, Pluto is technically one of these trans-Neptune objects as well. So there's a lot of remnants of this left over. And of course, the asteroid belt is by many people thought to be the result of such a process from the early formation, which it may well be. There's a lot of contention around the asteroid belt, what exactly it is. So, as the planets the hypothetical planets, which we infer from these ring structures, concentrate these dust particles into these clumps, those are actually much larger than the planets themselves, and so that's what we actually end up imaging in most of these cases. Let's see, this one actually we're looking up here. This star is called HL Tau. It's about 450 light years away from us. It's in the constellation Taurus, and the brightness of the ring varies with its position as it changes with respect to how we're observing it. So we get different angles of this thing. But sure enough, it seems like there are these gaps. And by the way, what we're imaging here is infrared, right? We're looking at the heat signature of these things. They're not glowing much in the visible spectrum. And of course, these things are embedded in gas clouds and so forth. So they're very difficult to see. You don't really tend to, when you look up at Orion at night, you basically see those 3 big stars and that's it. You're not going to see all of these little protostellar systems happening. They're mostly being forged. They're mostly being imaged in the infrared, which is, of course, our heat signature wavelength. Okay, so very recently, we started to conceptualize and visualize these things we call exoplanets. And that's what you can see up here on the screen. It's worth mentioning, though, that our poor martyr, Giordano Bruno, was the first person to really put forth the idea that the stars are essentially similar to the sun and that they're all accompanied by planets. And of course, he was burned at the stake for this idea, and it turns out to be absolutely true. Like I said, it's probably shocking to you, but if you had really pushed that idea even prior to the first observations, people probably would have pushed back against you because, again, it hadn't been observed. And that's really the hallmark of a scientific explanation, is that it's built on the things that we can actually see happening, which makes it a very, in some sense, reliable basis to build a story on, but it also inherently makes it an incomplete basis to build a story on. So this one out here, we'll come back to this star system later. But the first exoplanet wasn't detected until 1995. And, that cracked open a whole new range of questions, like how does our solar system compare to these solar systems? Can they teach us about planetary formation? How does the frequency of these exoplanets influence our conception of whether life exists throughout, or whether life occurs throughout the galaxy? And it turns out that actually, as we'll see in a moment, there's quite a few Earth-like planets, right? There's quite a few planets in that habitable zone, as it turns out. In fact, I believe that we'll find it's somewhere on the order of 1 per solar system, actually, which is far greater than people would have ever imagined previously. And so this is quite encouraging to astrobiologists and people who are concerned with understanding life outside of our solar system. And people aren't just interested in aliens. They want to understand if life happens the same way every time, or if it happens differently, right? Are other creatures going to look like us? Are the bacteria going to be essentially the same? Will they have DNA just like us? These are really interesting questions that can probably teach us about how life evolved on our own planet too, because actually getting a bunch of DNA to turn into a life form is a harder problem than you would think. Particularly forming the machinery that's able to take a DNA and transcribe it into something structural, like a cell that's capable of autonomous motion, is really an endless challenge for biologists who are working on evolutionary biology. And so understanding if it's happening similarly elsewhere is going to be wildly important. And so the discovery of exoplanets has opened up this field of inquiry in full. And you're now starting to see whole departments at universities devoted to exobiology, exoplanetary science, with the intention that eventually we'll be able to go out and reach these stars. So that's going to be pretty cool. All right, so how do we detect these exoplanets? Well, we can't really see them for the most part. In fact, this is of course a very rare occasion that we get this nice top-down view of a star where we can get a perfect infrared signature from it. Usually they're shrouded in clouds, in dust, their brightness is overwhelmed by the brightness of a nearby star. They're almost impossible to see directly. And so we have to use some other means. And there's basically two ways that we generally use to detect these exoplanets. And by the way, we found thousands of them at this point in the last in just 20 years. And there's two main ways we do that. One is that we look at how the orbit of how the motion of that star is being perturbed. Because if you have a pretty chunky planet that's flying around you, say like Jupiter, the center of mass between the sun and Jupiter is actually going to lie slightly outside of the sun's effective surface, right? So if you were to look at the sun and Jupiter from far away, you would actually see that they are orbiting a point that's not quite inside of the sun. And the result of that is that the sun appears to do this little wobble from a distance. It would look like this, very, very slight wobble. And so looking for wobble is a huge piece of how we detect exoplanets. And then once we start to detect them, maybe we can start to zoom in on them and focus on perhaps getting some sort of direct infrared readout or something. Another way that we can do it is by looking, we can look at that wobble not just through the positional, but also through the velocity changes of that planet, which is also another way of looking at its wobble, I suppose. And so we can break those down a little bit for you. All right, so, the radial velocity, the speed at which the speed at which the sun is twisting has some change that's on the order of 13 meters per second every 12 years, and that's just due to Jupiter. So we talked a bit about how you measure the radial velocity using the Doppler shift a couple of weeks ago. And so the idea, this is sort of illustrated up here, as the thing is kind of twisting away from you, it's going to be having, you're going to encounter less of those light pulses, those waves of light, per unit time as you would if it was turning towards you, right? And so you get a red shift on one side and you get a blue shift on the other. And this gives us the ability to look at the radial velocity of these stars. And it turns out that when there's a planet out there that's sort of tugging on it, it can actually change the dynamics of this in such a way that is deviating from the expected otherwise. And like I said, it turns out that most of the star systems display this to some extent. The first time that they used this Doppler effect was in 1995. Right? This is not that long ago. That's I guess I was in middle school, but that's not that long ago. And actually, they found this star which was in the constellation Pegasus, which is interesting. Of course, Pegasus. Well, I didn't even mention this last time, but when we talked about the story of the sea monster, right, in Andromeda. And Andromeda was this princess who was being rescued from the sea monster. The hero who comes in to rescue her comes in on this horse named Pegasus, which is quite interesting. And it's all sorts of interesting interpretations of what that means. But it's something like the inspiration that pulls you into doing what you should be doing, which is important. So, one of the first things that was really surprising to people was that the stars they were detecting were the planets they were detecting were really close to the stars. Something like took only like 4.5 days to rotate around the star. Okay, so very early on, we started getting the impression that the stars that the planets we were going to observe were special planets, right? We're going to see the things that are most easy to see first. This makes sense. It's sort of like it's part of this idea that our perception is not necessarily objective. We're just going to see what we're looking for. In this case, we're looking for wobbles. We're going to select for planets that are enormous and ones that are very close to the star because those are the ones that are going to perturb it gravitationally the most. Remember, gravity, just like light, falls off with an inverse square. That's really, really precipitous. It's so precipitous that if you go only a couple hundred kilometers above the Earth, or not even, if you go 60 kilometers above the Earth, you'll essentially feel like you're floating because gravity is such a weak force at that range, right? So we're selecting for a particular kind of planet when we studied these things. And this is really, really close to that sun, by the way, that distant sun. Mercury takes something like, I can't remember off the top of my head, on the order of 80 or 90 days to go around the sun, right? And it's very, very close. If you've ever seen a picture of Mercury next to the sun, it's very, very close. So these planets that we're talking about are not only much, much larger than Mercury, but they're also very, very close to the stars. Okay, this turned out to be a huge problem also because our understanding of how the gas giants formed prior to the discovery of exoplanets was something like this. The only place where gas is going to be cold enough to condense into a ball during this disk collapse process is far away from the sun, right? Think about Neptune, think about Uranus. If you were here last semester, you understand these are extremely cold places, right? They're made out of ice for the most part, but it's very particular. It's it's hard to call it ice, but it's not quite a liquid either, right? They're in this extreme state of matter that's under great compression and coldness. And so the only place that most people had believed for hundreds of years, including the 20th century, that this could happen was far away from the stars that they were forming around. Well, this immediately became untenable when we discovered exoplanets because we saw huge Jupiter-looking planets right up next to the stars, right? In fact, usually they were found there. And this was quite troubling, actually. And so the place that we're at right now, well, at least that we've been coming, that immediately, what happened, right, when people started discovering these? Well, they immediately said, okay, here's what happens. The stars form really far out still, like we always thought. We were right about that. But they just move inward as they go. And this is called the grand tack hypothesis, right, from sailing. These things change places, right? And as they do so, they create all kinds of interesting circumstances. And in fact, they smash together other planets, they disturb orbits, and you can get recombination, and you get some of the more interesting features. Maybe even maybe they organize the asteroid belt this way. Maybe they do away with smaller planets. They disturb them so that they fall into the sun is the idea. Because what's really interesting, we'll get to this in a minute, I'll show you a figure. We see a really interesting gap, right? We see a fair amount of Earth-sized planets. We see a fair amount of Neptune-sized planets, but there's a little gap there where we don't see as many of the size of planets that we should expect to find. There's no intermediaries. And so the astronomers have integrated this idea that the gas giants are moving around into explaining what happened to all of those mid-sized planets, right? Maybe they've thrown them off, they've messed up their orbits, they got eaten by the sun. So that was the rescue for this theory, but we hung on to it, and we still stand by this idea that the gas giants formed far away because it's the only place they could. And we'll try on some alternatives to that idea here in a minute. But I do want to impress upon you that we have this extraordinary selection bias, and of course the astronomers are absolutely aware of this, and they realize that, the Doppler shift method is only capable of looking at these big ones, that the Doppler shift is most adequate to looking at ones that are close, and so we can't really see if those Jupiters are forming far out. We wouldn't know because they're cold. You can't see them with infrared. They're not going to have a strong gravitational perturbation on the star system itself. All right. Did I skip one here? Okay, so back to this original image. This was actually this HR 8799. This was one of the first systems that we actually got direct imaging. And so, we can, like I said, once we see some of these perturbations, we can zoom in and start to look for the actual planets themselves. Now, this works best for planets, like I said, that have really young gas planets that are hot, that are nearby the star, that are emitting infrared light. And they can't be too close to the sun, because if they are, their light will just blend in with the sun. If they're too far away, then they'll be too cold. And so they're in this beautiful Goldilocks zone. So this really narrows down our ability to direct image to a few of these systems. There's a few features that fall out of this. We can see some of these thick clouds around it, which is quite interesting. When we actually look at these little pinprick planets, we actually see that they have something that approximates a nebulous form around them, which we assume to be gaseous clouds, right? That's part of the reason we think these are the gas giants. We can also look at the spectra, right? The colors that fall out from that, and we get an idea of their composition, and that also leads us to believing that these planets are hydrogen-rich. They're very similar to gas giants. There's some methane, some of the things we would probably find in Jupiter, right? So this is the sort of scatter plot of the different sizes of planets that we see when we look out there. And you can see the gap size there, which is quite interesting. So Earth is down there, it's number 1. You have a nice spread of planets up to like 4 Earth masses. I guess this is radii, Earth radii. Then there's a little gap between the Neptunes and the Jupiters. Now we call these things, most of the planets seem to be bigger than our Earth for the most part, the Earth-like planets before they become Neptunes. We call them super-Earths for the most part. And these turn out to be some of the most common planets in the whole universe from what we can tell. Although, of course, we're looking at something like a quarter of an arc minute of the sky in our own galaxy, which is, you know, something like an inconceivable infinitesimal amount of all of the star systems out there. But from what we can say from what we're observing, it seems like most of the planets turn out to be these super-Earth planets, which is quite interesting. And you know, some of these orbital periods of these planets are more similar to our Earth. They range from hundreds of days to 4, maybe 5 years, which is interesting. You know, the absence of planets smaller than Earth might be disconcerting, but then again, you consider that, well, we can only see the things that are big enough to either cast a shadow or they're big enough to radiate their own heat, which is separable from the planet. If something's too close to the star, like I said before, its light, its heat is going to blend together with the star. So it's very difficult for us to see something, say, the size of Mars, right? Or smaller, like a moon, or something like the size of Mercury, which is essentially the same size as our moon. It actually is it's very, very similar to our moon, which is quite interesting. All right, so you know, there's a lot of interesting evolutionary theories that have cropped up around this diagram, and I think this is starting to point us in the direction of where these things are heading towards the future. Actually, if you would go back and look at the literature prior to the discovery of exoplanets, the word evolution hadn't really made it into the astrophysical literature. I think this is actually a really exciting concept, that people are thinking about planets as perhaps changing their form over time in response to their environment, which is, you know, I would say a foundational principle in science that's making its way into everything from economics to astrophysics. And so there's some thought that's appearing in the literature today that suggests that perhaps the planets as they form go through different transitions. And the extent to that is not entirely clear. But if we look at our own history on Earth here, and we look back to what we can tell, we know that the Earth in the past was wildly different than it is today, for sure, right? I mean, let's just go back, you know, our rock record goes back only about 4.5 billion years. But let's go back just maybe a scratch of that, a few percent of that. Let's go back, say, 70 million years ago, right? There was animals as big as this auditorium on our planet just thumping around, right? The dinosaurs. So, you know, there's serious physical problems with the dinosaurs, actually. It's actually a very intriguing thing to start to study about. Because, you know, the ability for these massive animals to support their own weight by itself is troubling, right? Actually, if you take something enormous, like a whale, and you put it on land, it's going to have a hard time because it's going to be crushing itself, right? In fact, the biggest animals we have, like whales, for instance, they exist in the sea for good reason, and that's because the upward force of buoyancy counteracts gravity, and so they don't get crushed to death, right? But the dinosaurs, how does that work out? There's also these interesting animals at the time which aren't quite dinosaurs. I think they're called Quetzalcoatli. They're these giant flying dino type things. They're the pterodons, right? Well, they don't really work out physically in terms of being able to fly. They had these big wings. These things were the size of an airliner, but they weren't physically capable of flying in the sense that we understand it today. In fact, if you process wing size and you plot wing size and mass on a diagram, you can actually get a very nice fitting line, right? You can fit jumbo jets on it and, you know, pelicans and everything you want, bugs, whatever. these pterodons didn't really fit into it, right? And so all of this suggests to me that the environment back then was very different, right? And we don't totally understand it, but we know that something was different, right? Something was radically different about the Earth back then, you know. And one possibility, actually, I had the real privilege of sitting down with this really interesting astronaut named Donald Petit. He's still an astronaut, actually. He's going back to the space station soon. And he actually did his PhD up at University of Oregon. And he worked under this gentleman named Levenspiel. And Levenspiel had this idea, and Don developed it to some extent, that perhaps the atmosphere back then was much thicker than it is today. In fact, it was so thick that it was kind of approximating on something. Again, the phases of matter are quite confusing, but it was approximating something more like a fluid. It didn't have a different composition, and there's the same amount of oxygen, the same amount of carbon dioxide, the same amount of everything, right? Mostly nitrogen. But it was so compacted and compressed that there was an upward buoyancy force which was able to support the weight of some of these beasts, which is really interesting. Okay, so whether or not that's the case, we have the idea that our Earth goes through tremendous changes. Certainly everyone will agree that during the time of the dinosaurs, there was no ice on the polar caps of the planet, right? There was tropics, actually. You can see fossils down near Antarctica that are tropical in nature. This is very bizarre, right? Well, actually, it makes a lot of sense if the atmosphere is extraordinarily thick because, of course, you have all of the wonderful results of that sort of greenhouse situation. But even if that wasn't the case, we know the Earth was very different. And there's no reason to believe that all of the planets also haven't gone through interesting changes along the way. And so there's this idea of planetary evolution that's starting to appear, which is quite fascinating. It's very much in contrast to the perfect ordered world of, hey, the planets got made like this, they still look like this, and they'll always look like this until the star explodes, and that's it. And I think that that's something of a very rudimentary and quickly outdated perception of how these things work. And unfortunately, it's the perception that has stuck with us for hundreds of years, and that's probably why it's highlighted so strongly in your textbook. But of course, as with any old idea, there's also some really beautiful grains of truth in it which must be integrated. Now, I wanted to just show you guys this. When we first started looking for exoplanets back in the 90s, this was the little sphere around our star system that we were capable of looking at, which was about 200 light-year distance. The new Kepler search program is looking like, a whole order of magnitude further, although it's only able to look at a little window of the sky. So I think that's a pretty cool illustration of just how people have decided to focus their attention. Instead of focusing on the things around us, which could be misleading, right? Because maybe we're in a particularly interesting, we're in a unique environment here, and so our planets form in a different way than everybody else. So they decided to focus on a small sliver of the sky, but to go very deep and look at all of the different systems within that, which seems like a much more reasonable way of going about things. All right, so this graph here shows the number of planets in each size range that are found amongst the first 2,000 or so Kepler discoveries. And much like on the graph on the scatter plot that I showed you, the sizes here range from our Earth size to something like 20 times the size of Earth. And so the y-axis here shows the fraction of each size that makes up the total body there. And we'll talk a bit about how we know essentially from the size, the angular size of those planets, and from their orbital dynamics, we can get both their physical radius, their size, and we can get their mass. And from that, we can calculate the density. And from the density, we can get an idea of what they're comprised of. Because obviously, you can't build something very dense out of something that's an element that's quite light, or molecules that are quite light. And so this allows us to break them up into some bins like we would expect on Earth. Our rocky planets, which isn't quite a fair term, because when we say rocky planets, we actually mean they're very metallic, in fact. They're more like chunks of metal than chunks of rock, although there's quite a bit of silicon too. There's silicates, I guess. And then we have, the icy ones out here, and then we have our gas giants. But interestingly, we don't see these ones in the middle, like I was saying, in our own solar system. And so this has, of course, led to this rush of literature lately trying to explain what happened to the planets in our solar system that should be accounted for in these other systems, because we're missing these super Earths, actually. So what happened to the super Earths in our own solar system? And, most of the explanations concern those super Earths getting disturbed, getting eaten up, getting swallowed by the sun, something like that. I'm trying to put forth the idea that maybe they've evolved, actually. Maybe the super Earths were something like between a Neptune with a huge atmosphere and something like our Earth with a very thin atmosphere, or like Mars or like Venus, right? With a very thin radial atmosphere. Of course, Venus has a very thick atmosphere, but it's relatively shallow. And so, there's also the potential that these planets evolve towards one another, which is quite interesting. Now, the timetables necessary for that are a different challenge altogether. And so I think that's why it's not more readily embraced at the moment. Let's see here. So we have to kind of correct for this sampling bias. So what we do is we see the most common planet sizes are the planets that are about 1 to 3 times the Earth, these super Earths. And that this group is, each one of these groups is occurring in something like a third or a quarter of the stars. And anyways, if we group these sizes together, we can essentially conclude that there's at least one planet per star. So all of the stars that we're aware of should have at least a planet. Now, we can't really say if there's planets that are a great distance from the stars, so it's probably a lot more. Again, if those Jupiters are indeed forming out of the protostellar disks and they're far away, we'll never be able to see them, so we can't account for them in our tallies here. So when we try to estimate the number of Earth-sized planets in our galaxy, we have to think about this, and we have to think about the fact of what sort of stars would even be capable of hosting an Earth. So we look to these F, G, and K type stars, and there's about 100 billion of those. And then we estimate that maybe there's 30 billion Earth-sized planets in the galaxy. So this is interesting because it means that there could be something like 100 billion Earth, super Earth type things in the galaxy. And so the planets of essentially our size are quite numerous, as a matter of fact. And this has actually been one of the most shocking discoveries, I think, since this advent of exoplanet sciences recently. All right. So, for several hundred of these exoplanet systems, we're able to, like I said, look at the size from the transit data and the mass from the Doppler data, from the gravitational data, and we can get this idea of its density. And then we compare the average density of the exoplanets to the density of planets in our solar system, and then we put them on this map. And we can lay these out on something, on a graph that looks something like this, and we can actually distinguish which one of these clumps of planets relates to these different compositions. In reality, the planets are actually these layered complex entities, and so this is a real first-order approximation. No planet is exactly water, only water, and no planet is exactly iron. They're all these wonderfully onion-layered structures that have pieces of each one of these. So these lines here, these theoretical lines, are just guides that suggest a range of possible compositions. And you can see that there's 2 green triangles there. One is Earth-sized and one is Venus-sized, which is right there, down kind of in the center bottom. And, all these planets fall between the model of a pure iron and a pure rock planet, which is kind of consistent with what we would think for the composition of Venus and Earth. These planets also seem to have eccentric orbits. They're not in perfect circles, which is quite interesting. And this process results in all sorts of tidal interactions between the bodies, which can inflate, stretch, make the atmosphere expand, pull it off. And And so this is really important when we put the error bars on our radial calculations for how big these things are. It also tells us that the atmospheres of these planets are in constant flux. I think that's really important. In fact, we can now go out, and I think that I'll show you a picture later, but we can go and see that these Jupiter-type planets, call them hot Jupiters when they're that close to the sun, they're losing their atmospheres at extraordinarily appreciable rates because the wind from those stars is just cooking them off, right? And imagine just putting something, a cold ball of gas up next to a furnace. It's just going to evaporate, right? And so these changes are happening, right? The question is, to what extent have they happened in our own system? And this is really the future of planetary science, from what I can tell. Oh, my pen has stopped working. Let's pop it back in. Does anybody have any questions over what I'm talking about so far? Yeah? Come on. Technology is wonderful until it stops working. It's sort of one of those interesting things where you don't have to actually understand how it works until it breaks. All right, it's not going to work for me. We'll have to use the laptop. All right, so let's look at, we're going to look at this Kepler system, which is one of the best characterized solar systems that we've seen. And in particular, this green zone, which is being compared here to our solar system, just down here, is considered the habitable zone. And of course, the habitable zone is extremely interesting to the exobiologists because this is sort of the one region where things are cool enough to not be cooked, but they're not so cold that the water is going to leave the liquid state. Yes?
Is there a difference between the habitable zone and the Goldilocks zone?
Usually, that's a good question. I think that they're synonymous. I'll have to get back to you on that. I've usually heard the Goldilocks zone with reference to a place in the galaxy, but the habitable zone usually with respect to solar systems. But yeah, that's a good question. I'll have to get back to you for sure. So what we're looking here is Kepler 62. Almost all these planets are larger than Earth. These are super Earths, which is a very common type of exoplanet. One of them is actually about the size of a mini Neptune, and it's thought to be largely gaseous, but it has a composition which in some sense is overlapping with the Earth, right? So this is an interesting sort of, in a sense, it's something like a Darwinian missing link between the Earth and Neptune. And of course, we're missing these in our solar system. And I think this is actually really critical because the models that we came up with and that we were using into modern times, well into the 20th century, into the 90s, had one data point, which was our solar system. When we look at our solar system, we don't see anything that is in between an Earth and a Neptune, right? And so it's not startling or surprising that the models we came up with for how our solar system formed didn't have any sort of evolutionary progression between the two, right? We didn't have those missing links, but they turn out to be highly abundant in systems like this Kepler 62 system. Anyways, what do I want to say about this? Most astronomers thought that planets would be found only on single star systems. But actually, that turns out to not be the case at all. If you'll think back to the beginning of the course, we said that almost all stars are found with a partner star, right? In fact, many of them have 3 or 4 of them living as a family together, right? And all of those have planetary systems as well, too, which could get quite chaotic and confusing, actually. You can imagine your orbit interfering with the orbit of another planet could be a serious problem. And it actually kind of boggles the mind for me to that, well, I suppose it comes down to the fact that these discoveries are so very recent. I don't think I can impress that upon you enough. Most of the things you're going to learn in science class are things that have been developed over hundreds of years, chemistry, physics. This stuff is brand new. It's hot off the press, right? But if you think about all of these planetary systems so close to each other interacting, what are the odds that some of those planets are going to have completely chaotic interactions, right? They're going to be at least tugging on one another. You have to think some of them are occasionally going to get completely dislodged from their orbital circuits, right? It's just inconceivable to me that that wouldn't be happening all of the time. We know, for instance, that stars are crunching into each other quite regularly. In fact, these binary systems eventually almost always will result in the merger of these two stars. One of them is thought to be bled off by the other, but they interact, right? So why shouldn't the planets be interacting as well, since all these stars have planets? And so, you know, I think that I want to at least open the idea to your imagination that it's possible that some star systems, some of these planetary systems, forge planets, and maybe some of those planets leave those planetary systems and they end up in a completely different planetary system. And that's a thing for which we have absolutely no evidence of, right? It's not going to make it into our scientific narrative because no one's seen it happen. But what are the odds you're going to see that happen? They're cold, right? You can't even see the Jupiters that are too far away, that are outside of a few, AUs from the star system that they're close to. We don't know. It's a blind spot. But it seems to me inconceivable that this isn't happening all of the time, actually. You know, and I asked my friend, who's a planetary scientist studying these things at Caltech, Constantine. I asked him if if anyone was concerned about this, and he sat there for a minute, and he said, "Well, I guess it's possible, but we don't have any evidence that it's happening." Yes.
CHA 11091, big long ass numbers. Isn't that considered I just Googled it.
A rogue.
Rogue planet?
Yeah, rogues. Yeah, I'm glad you brought that up. So indeed, so so rogues are, yeah, I don't know that particular one that you're talking about, but rogue planets are a fascinating theoretical idea, right? And so the evidence, I wish I'd actually prepared more information on rogues now that I think about it. But rogues, depending on different gravitational estimates, it's thought that there could be as many as, hundreds to hundreds of thousands of rogues per planet that we see. Planets that are just out in the foam of interstellar space, right? And of course, these are impossible to detect for the most part. Of course, maybe they've seen a couple that are on the brown dwarf end of things. They have some residual heat from their formation, or they're crunching a little bit of fusion. There's a bit going on right now, maybe some deuterium fusion like in brown dwarfs, so they give off some heat signatures. But for the most part, if there's something like, let's say, a Mars that's floating around in interstellar space, you will never see it. And so there's some controversial papers that have appeared that suggest that there could be hundreds of millions of these things everywhere. In fact, interstellar space could be just absolutely chock full of these things, right? Now, I think that is really, I want you to hold on to that idea. Okay, we are very close to having to run out of space here. And so maybe it's time that we jump to the point of all of this. Look, if there are, in fact, lots of rogue planets out there, then we're going to have to move towards a planetary formation model that invokes the possibility, at least, that planets are spending time in different places, with different stars even, perhaps, right? Now, this is interesting because if you think about the fact that the core of something like a Neptune actually looks a lot like an Earth to begin with, right? The composition of the interior of some of these planets is quite similar to what we have on Venus, on Mars, on Earth. And all of the weight of that atmosphere is actually capable of crunching something down to the densities that we would expect on Earth, right? It's a serious problem how you jam something together that's as small as Earth in such a small space, right? Why isn't it inside of a star, for instance, right? This is very troubling. Now you add that on to the problem of the angular momentum issue, right? If our planet formed with our star system, why is the star not rotating way faster than the planets? If you add that on to the pebble problem, the meter-sized barrier in the accretion models, why is it that you get something as dense, as big as a planetesimal, but you can't stick pebbles together? And the answer, I personally, this is just entirely my opinion, and probably no one will jump on the bandwagon with this for 10 years or 20 years, but it's going to happen. One of the easiest ways to do that is that the planets evolve, and they evolve by spending time in different places, maybe even different star systems, They go through transitions much like organisms. They evolve with different shapes, right? A baby is not a baby forever. It turns into an adult eventually. An old person doesn't start out looking like an old person. They were a baby once as well, right? And so this idea of evolution is almost inevitably going to be applied to the solar system to solve these problems that we've been wrestling with for hundreds of years, right? And things don't change easily. This is, if you go out and suggest this to someone who's spent their career working on the nuances of that 300-year-old system of planetary formation, they're not going to be highly interested in the idea that there's a different way of looking at this. And so this is one of the challenges with science, is how do we open our minds up to discussing things which seem completely heretical, to the things that got people burned at the stake in the past, right? We still do that to some extent, right? This is a wonderful opportunity because we don't actually have an astronomy or an astrophysics or a cosmology department here. So we actually have the luxury of exploring ideas which might be somewhat heretical. And this is one of those ideas. And so I want to be absolutely clear to you. This conception that I'm trying to paint for you about the future of science, the future of our understanding of the solar systems, in some sense, it's quite comforting because it makes a lot more sense than the one that we're left with in the textbook. But it is by no means an accepted idea. And so I don't want you to rush out into the streets and say, Dr. DeLay told me this is how planets work. Well, it's just a possibility as far as I'm concerned. I don't actually know the answer, and I don't think anybody does. So let me make sure there's absolutely nothing else that I wanted to tell you today. I think the bottom line is that we've come from a place where when we looked out at the heavens, we wanted to ascribe a maximum degree of order to them. And we do this with nature too. There's this interesting paradox in our own society today where people will often ascribe this fallacy that nature is this wonderful utopian place where everybody treats each other nice and it's very ordered and happy. And if we could just get back to it, if we could just throw off the tyranny of our oppressive social structures, that we would, get back to nature and everything would be fine. But I think the reality of the situation is that nature is full of chaos and full of all sorts of unsettling features, right? I think that this principle is slowly being entertained in terms of the way that the star systems organize themselves and the planetary systems organize themselves. And it's not necessarily a happy thing to consider, right? It's not fun to think of the fact that, hey, if the Earth flies off its handle, if Jupiter changes position and our orbit is destabilized, what's going to happen to us? Well, it's not necessarily a good thing for us in the short term. But, I did the calculation last night at dinner. I was kind of discussing this with my wife, and we thought about it. The Earth is moving at about 100 kilometers per hour around the solar system. If it flies off of its leash, so to speak, its gravitational leash, and it just goes off into interstellar space, how long would it take to reach the next star system? Well, you might think it would take too long, and so, that's probably never happened before. Okay, fair enough. But if you do the calculation, you find that you could actually reach Proxima Centauri in something like 45,000 years. That's not that long, actually. And we know for a fact that the Earth has been completely covered in ice for no apparent reason, kilometers thick ice for significant portion of its. This is called snowball Earth period, right? We're also missing entire billion-year sections of the geological record. Crazy things have happened on this planet before that are completely unpredictable and inexplicable. And the integration of those events into our planetary formation models is inevitably where these sciences are tending towards. So I can't promise you the answers, no one can, but at least we have some idea of how these gaps in our understanding, which are so well elaborated in your textbook, might be addressed in the future. All right, you guys have a great weekend. I'll see you next week.